Dear colleagues, welcome to this Keynote lecture. It is my great pleasure to introduce Manuel Mazo. He graduated from Polytechnic University of Madrid and has a degree in telecommunication engineering, and also in parallel from KTH, Royal Institute of Technology in Sweden. Then he joined UCLA, where he received master and PhD in electrical engineering. And now Manuel is an associate professor at Delft Center for Systems and Control, where I had the pleasure to work with him for several years. So I think you already can see the title of Manuel's talk. It remains me to give the floor to him. So please, Manuel.
Thank you, Anton, for the introduction, and thank you all for attending this keynote talk. So today I would like to talk to you about how one could use time automata and actually automata in general to bridge the efficiency and predictability of event trigger controllers. And I hope that through the lecture, what I mean by bridging efficiency and predictability of event trigger controllers becomes somewhat clearer. So the outline of today's talk is going to be, first I'm going to start with an introduction, as many of you probably are not familiar with event trigger control. So I'll introduce what's event trigger control and revisit what are the promised benefits and why one defends the use of event trigger control. Then I'll proceed to state a couple of problems that I think are important to address when it comes to event trigger control, and those are related to scheduling and analysis. And hopefully my motivation will become clear why these two problems are very important to be addressed. And the next thing that I will do is introduce a couple of modeling frameworks, which I will use then to solve those problems in the fourth part of the talk, which will be dealing with a couple of problems, mostly regarding scheduling, analysis, and some design of improved event trigger control designs. And finally, I'll conclude showing some ongoing work and plans for future work and the kind of things that we are hoping to achieve in the shorter term. So without further ado, let me start with a brief recap on event trigger control. So if you look at nowadays control systems, these are typically implemented as the picture that you see here on the left. So usually you have your control plant, usually modeled as some form of ordinary differential equation, and you have a controller implemented in a digital device. And the way in which you close the loop is through some sensor that takes measurements at some time instance Sk. Then when the measurement is acquired, it's sent through possibly a communication network to a controller, which computes a control action, sends it to the actuator, and the actuator holds this input constant until a new measurement is sent and the computing device is, the controller is recomputed. Now, on the other hand, control engineers design their controllers oblivious to this implementation. Usually you assume or you ignore the fact that you have this sort of sample and hold implementation, and you just simply design some feedback map, K, which you assume that is going to be somewhat implemented in continuous feedback. And one designs controllers to guarantee certain properties of this closed loop ordinary differential equation. Now the question is, how can we ensure that our practical implementation behaves somewhat like what we designed? And typically what engineers will do is, well, we'll implement this cycle, we'll close this cycle periodically fast enough. And fast enough tends to be as fast as we can. Now, the obvious drawback of such implementation is that the demands of resources by this controller implementation are oblivious to the state of the system. So your controller or your communication system will be transmitting samples independently on whether the system is stable, and therefore the transmissions that you're communicating do not have an impact on the recomputation of the control action or not. Now, to address this drawback, the idea of event trigger control is to introduce feedback in the sampling mechanism. And what do I mean by feedback? Well, assuming we have sensors with some amount of communication capabilities, we will let is the sensor decide, based on the measurements that is taken, whether a sample is interesting to be sent to the controller to recompute the control action or not. And by doing that, what we will obtain is a form of aperiodic sampling. Now, maybe the system will be sampling very frequently when the system is very unstable or requires a lot of corrective actions. And as the system starts becoming, reaching its equilibrium point, maybe you can start relaxing how frequently you send measurements. Now, the expected gain is that by sending less samples through the network, you will reduce, obviously, bandwidth usage, and also potentially energy usage if this network is some form of wireless network where devices consume energy by transmitting messages. So let me zoom in a little bit more onto event trigger control for those not familiar with these ideas. And let's look at the simplified version of the problem. So I have, again, my control plant, a sensor that is going to be sending measurements represented by closing the switch at some times sk, a controller that, based on those samples xk, computes an input uk, and then these inputs are sent to a zero-order Hall, the actuator, which keeps those inputs constant until new measurements are received and new control actions are recomputed. So in that sense, the control action that is seen by the plant looks like some sort of staircase where the steps of the staircase are variable in length. For instance, between T1 and T2, maybe 200 milliseconds elapsed, and between T2 and T3, maybe 400 milliseconds elapsed. Now, an alternative way of modeling is by replacing this switch by some form of virtual error signal that is being added to the state of the plant that is feedback continuously. So now we basically assume that what we have is a continuous feedback, but it being affected by some virtual error signal due to the sampling mechanism. And obviously, this error signal will have a very particular shape. And what do I mean by this particular shape? Well, first off, it will be somewhat symmetric to this the state of the plant. And every time, so that the addition of psi and epsilon will give me essentially a constant like this. And every time I take a new measurement, then this error signal will automatically become zero. It will be reset to zero, because at those points in time, then both xk and psi-k coincide. Now, by doing that, one can do some not too complex analysis and come up with conditions that this combination of signals, psi, the state of the plant, and epsilon, this virtual error signal, need to satisfy to guarantee that this closed loop system, now in this sample and hold form, is rendered asymptotically stable, and moreover, guarantees that some prescribed performance is enforced. Now, that is one example of such a condition will be the one that is written over here. So if we can manage to keep the ratio between the magnitude of this virtual error and the actual state of the system between some constant sigma at all times, then we will get the desired asymptotic stability and prescribed performance. Now, interesting to notice is that now the only way we have to enforce this condition is by manipulating epsilon, by deciding when we sample. But fortunately, by deciding when we sample, we can reset the error epsilon to zero, and therefore will be below this constant sigma. So let me illustrate this a little bit better with a little picture. This ratio over here is this blue line, and sigma is this constant red line. By the way, sigma will depend on the prescribed performance that one wants to achieve and on the exact system dynamics and control that one has at hand. Now, what will happen is that the sensor will be observing this blue line. Whenever the blue line hits the red one, then it will decide that a new measurement needs to be transmitted. So that this blue line is reset to 0. And we guarantee that this condition is satisfied, and therefore we know that we retain asymptotic stability and the desired prescribed performance. Note that in this whole discussion, I'm assuming that the controller is already given. So all I'm doing is designing a triggering condition to decide when we're going to be transmitting measurements. Now, that will usually result in patterns like this one. This is coinciding with this simulation over here, in which initially, when my system required a lot of corrective actions, we have sampling times very small, and the height of these bars are basically the distance between 2 consecutive sampling instances. And as the system starts getting closer to its equilibrium, these times start growing. Now, so to recap very briefly, basically in event trigger control, what we will have is that the sampling instances Sk will be somewhat a function of the state of the plant and the previous samples transmitted, and possibly also the times at which those samples were transmitted. Now, a simple example is the one that I showed you, where it only depends on the current state of the plant and the last sample that was transmitted, and that is because with the last sample and the current state of the plant, one can compute what's the value of the virtual error signal epsilon. And in that form, then it is obvious to see that the sampling sequences are dependent on the plant state. Now, a variant of this is what we will call periodic event trigger control, in which essentially you set a clock on the sensor so that the sensor can only take measurements at specific points in time, and therefore these sampling instances, or these times at which measurements will be transmitted, will also be just proportional to the sampling time at which sensors are taking measurements, and let's call that h. Therefore, now our phi PETC determining Sk will give me some natural number multiplied by h as the sampling times. And this will become useful in some of my discussions later on, but you can also imagine that this comes a bit closer to what will actually happen in practice, where sensors also nowadays are usually digital and therefore are taking measurements periodically instead of just continuously over time. By the way, feel free to raise your hand if at some point you want to ask a question. Given the format, we can make this maybe a bit more interactive. Now, so let me go back to the benefits of event trigger control. So if one looks at the literature, at least historically, the most cited benefits users' motivation for event trigger control were the reduced bandwidth use and the reduced wireless energy use. So let me focus on the second one to try to illustrate what is meant by reduced wireless energy use. Let's take a very simple example in which I have only one sensor, an actuator attached directly to my controller, my plant, and I have some network transmitting the measurements from the sensor to the controller co-located with the actuator. Now, we will talk about reduced wireless energy use in the sense of the energy that this network is using, and that energy use will be proportional to how many communications is delivered, how many transmissions it has to deliver. Now, so in periodic control, what you will have is that every T seconds, the whole system wakes up, measurement is sent, the controller computes the control action and applies it to the plant. Then it goes to sleep. T seconds later, the same thing happens. Goes to sleep. T seconds later, the same thing happens. In event trigger control, things look slightly different. First, your system is asleep, At some point, your sensor will detect, hey, my triggering condition is violated. I need to send a measurement to close the loop. At that point, the network will deliver the measurement to the controller, which will compute the control action and apply it to the plant. Then your system will go to sleep, possibly for a long time, until again, a new event happens and the cycle repeats. But now, note the question mark over here. Do we really reduce wireless energy use? And this is the elephant in the room, is the following. Whenever a new event is triggered by the sensor, the question is, who's listening? How does the network know that it needs to be awake in order to transmit that measurement? Now, let's make our life a little bit simpler. That's why I introduced this idea of periodic event trigger control. If you're doing things based on periodic event trigger control, that problem of who's listening is somewhat simplified, right? Because what you will do is the following. Every T seconds, the sampling time selected for the periodic event trigger control, so the sampling time at which the sensor is taking measurements and potentially will be transmitting a measurement, the network wakes up. And there was no transmission, there was no event at the sensor, and the network goes to sleep. Again, 3 seconds later, it will wake up, see if there's something to be transmitted. If there's nothing to be transmitted, go to sleep. And it will repeat this process until at some point, when it wakes up, there's an event to be transmitted, a sample to be transmitted because an event happened at the sensor. At which point everything is awake, so the sample can be transmitted, the control action can be recomputed and applied to the plant. Now, for the ones of you that paid a little bit of attention, probably you notice that even now, with this simplified case of periodic event trigger control, we're only saving transmission energy with respect to a periodic approach, right? So if I would have had things running periodically, my network would have been waking up periodically, as in this case, and every time it will have waken up, we'll have had to transmit some message. But in both cases, the network is listening for about the same amount of time. Every 3 seconds, the network will be listening both in a periodic approach and in this periodic event trigger implementation. And for those of you a bit familiar with wireless communications, you will know that Rx receiving energy consumption is typically of the same order or even larger than the energy that a device consumes in transmission. And if you don't believe me, I took just the specs of the CC2420 chip used for 802.15.4 protocol, and you can see here low current consumption Rx 18.8, TX 17.4. That means that waking up your network to listen consumes more than when the network is transmitting. Now, let's go then to the other case. How about reducing bandwidth use? Well, I would argue that as with scheduling listening times, now we have a problem to schedule transmissions to avoid packet collisions. And why do I say that we have a problem here is because if we want to schedule two control loops that are transmitting in a periodic fashion, and we don't know when will they be transmitting, then we have a problem in trying to predict how to schedule them so that they don't try to access the channel at the same time. By the way, I hear noise all the time on the background. If somebody has their microphone on, would you mind switching it off? Thank you. Okay, so we were saying, similarly to the case on reducing wireless use, when we are talking about reducing bandwidth use, we have a problem because as we don't know when transmissions may happen, we essentially need to save bandwidth for just the possibility that a transmission may need to take place. So this brings me to the second part of the talk. I would like to establish now clearly what are the problems that we will need to solve to bridge this sort of gap between the promised benefits of event trigger control and these problems that I just illustrated. The first one will be a problem that I will say is a problem of synthesis, and it will become clear in the next slide why I'm talking about the synthesis problem, and it's the problem of scheduling. How do we schedule medium access of a periodic event-based controllers for both these two cases that I discussed, reducing energy in wireless systems and incorporating multiple event trigger controllers in a shared channel. And I will focus mostly on that second bullet where this becomes more apparent. Why did I say that this was a synthesis problem? Well, I'm a controls guy, right? I'm not really a scheduling guy, but as a controls guy, I tend to look at every problem as a controls problem. And to me, a scheduling problem is just one peculiar way, one particular form of a control problem. And what is the control problem in this case? Well, you have two control loops. Your scheduler will be essentially a controller that will send some scheduling commands to these control loops to prevent that both of them access the channel at the same time. That is, to prevent that some unsafe set is reached by the timing of those two systems. And at the same time, we want to ensure, of course, stability of the close of the control loops. Now, even if we ignore this problem of scheduling, there's some analysis problems of event trigger control related to this discussion that I just showed you that will still be interesting to be addressed. So in particular, one may wonder, if I give you two different event trigger conditions, which one will give less resources utilization? That's not an easy question to be answered. And it's a question that it was not really addressed until very recently. The second one will be, well, not only just compares two different event trigger controllers, but even if I give you just one and I need to dimension my communication network, can you tell me what is going to be the worst case utilization? And furthermore, could you even tell me that this event trigger mechanism is in some sense optimal? Now, so given those questions, let's establish another problem that I will be addressing in the last part of this talk, which is a problem of analysis and slightly also synthesis, which will be that of computing performance metrics for an event trigger control system. And not only we want to compute performance metrics, but we will also ideally be able to modify our event trigger controllers to try to optimize those metrics by modifying the triggering mechanism in some way. So now let's look at what is the essence that all these problems share with each other. And to illustrate this, let me show you this little cartoon of how I see the interrelation between control and scheduling. Usually in practice, there's the separation of concern between the controls engineers, here represented by the guy holding the gearbox, and the real-time engineers, the scheduling guys, here represented by the guy holding the watch. There's this wall. Each of them do their thing. The control engineer designs the control systems, ignoring how they will, or mostly ignoring how they will be implemented in practice. The scheduling guy gets some specification of what type of communications he or she needs to fulfill in terms of communication constraints and timing, and he deals with that system. And now, usually there needs to be some sort of abstraction that is shared between the two of them, right? And if you think about a periodic control, the interface by which these two guys will communicate will be a model that is as simple as saying, my controller needs to be running with this period, faster than this sampling time. Oh, sorry, this sampling frequency. And maybe there's also some, of course, there will be also some sort of maximum delays attached to it. Now, this, in the case of event trigger control, cannot be as simple because we don't have now a period that could be communicated to the other side. So we will need some form of dynamic model that represents what is the timing of the communications that an event trigger controller will be requiring. And And exactly this timing model is what a real-time engineer could use to enable scheduling, be it of listening times or be it to avoid collisions between multiple systems accessing the same shared communication channel. Not only that, those timing models will be useful if we want to do some analysis and potential design of event trigger controllers to compute those metrics that I mentioned earlier on and optimize those metrics that I mentioned earlier on. So let's then get to exactly that problem. How do we model the timing of event trigger controllers? And let me start first by introducing some basic modeling framework, and then I'll dive a little bit into time automata as those models and how could we construct such models of event trigger control timing in the form of time automata. Now, so the first notion that I will be using is the notion of generalized transition systems. And a generalized transition system is nothing but a sextuple indicating all the ingredients that one needs to provide in order to determine how a system evolves. And those ingredients are basically saying, well, in which set of states this system evolves, a set potentially of initial states, which in our case will basically be the same as the set of states, because in control systems, usually you can start anywhere in your state space. A set of inputs, and then a transition relation, which is telling us how systems evolve. So given an input from and a given state, where is the possible next state at which you will land? And note that this is a relation, meaning that from a given state, in general, this is a very general modeling framework. From a given state with a given input, you may end up in multiple places at the same time, just to represent some sort of non-determinism. And this will actually happen in some of the models that we're constructing. Then we'll have also a set of outputs, and of course an output map telling us how you map states to outputs. And just a couple of remarks. I will talk about a system being finite if X, the set of states, is finite. And this will become important when we try to establish models on which we can do proper computing automatically. Sorry. And we will say a system is autonomous if there's either only one input or no input possible. So let's get to what will be the interesting model that we will want to use as an interface between control engineers designing event trigger controllers and real-time engineers on the other hand. And for this, I need to introduce a little bit of notation. So let me denote by tau of X the next sampling time that an event trigger controller will generate when initialized at a given state X. So tau of X tells me if X was the last sample that was transmitted, the next sample will be transmitted after tau X amount of seconds. And psi sub X of tau of X will be, well, here we denote by psi sub X the solution of my control system initialized with initial condition X. So psi of X at tau of X will be the state of the system at the next sampling time, meaning the next sample, right? So psi of X tau X will be when the last sample was X and you trigger after tau X seconds, your next sample will be given by psi of X of tau X. Now with that, now I could write down what will be the system that will capture all the possible sequences of intersample intervals generated by an event trigger controller. And bear with me for a little bit. So this system will be, well, what the state space will be Rn, the state space of my control system. As I mentioned earlier, I will assume the initial set will be all Rn also. And now what's more interesting is what will be the transitions of this system. And these transitions will be, well, if you start from state X, if you're state X at a given point, that meaning that's the sample that you just transmitted. The next sample, X prime, will be the one given right? So you will have a transition between x and x prime, even only if psi x of tau x is equal to x prime, right? What I was explaining over this box up here. Note that this system doesn't have inputs. This is a closed loop system. This is an event trigger controller with where things are already closed. So there's no inputs to discuss here. And what will be the output of this system? Well, the output will be a subset of the positive real numbers, and what we will use as output is exactly tau of x, meaning at a given state, the output of my system will be telling me what is the next sampling time, or the next inter-event time. Now, one thing to notice is that this is a very nice theoretical construction, but this system still evolves over Rn. So it's an infinite system, and therefore, it's not only an infinite system, it's actually defined in a somewhat implicit and very obscure way. So it's very hard to automatically or algorithmically manipulate this system for any purposes. The next thing that I will introduce is the notion of time automaton. And instead of boring you with a formal definition, which you can find in this paper cited below from Allure and Deal, let me illustrate this more graphically. So time automaton is a form of hybrid system in which what you have is a number of finite locations from which you can establish transitions, and these transitions will be dependent on clocks. And that's why I say that this is a hybrid system, because you have discrete dynamics that evolve over this set of locations, but you also have a state, which is a clock that evolves continuously, following the obvious differential equation C dot equals to 1. Now, this time automaton has a number of additional ingredients besides the clocks and the locations, and is invariant, as you see here below each of the locations, which tells us in this location, the system may remain in this location for as long as this invariant condition holds. And then you have guards for each of the transitions that tells you the system may take one of these transitions whenever this guard condition holds. And then you have also resets. So whenever you take a transition, a discrete transition between locations, the clocks may be reset. In this case, they're always reset to 0. And you can even enrich this model, adding some sort of actions which act in the form of a guard by enabling or disabling. So if this action is present, action 2, then this transition is enabled, and it may take place whenever this guard also is active. Now, as I was saying, this is a hybrid system because it has both discrete locations, but also continuous state, which is the clock. But fortunate for us, this is a class of systems where state reachability is decidable. And for those of you not familiar with decidability or computing theory, this means that there are algorithms that will terminate in finite time that can answer questions about reachability of this class of systems. Now, what are we going to do is taking inspiration from the correct by design synthesis cycle, which for those of you interested, you could look at the book reference here at the bottom. Essentially, in the area of correct by design synthesis for control systems, the idea that has been followed is to use abstractions. Meaning we have maybe some hybrid dynamics that may be very complex, involving continuous dynamics and discrete dynamics interacting with each other. If we could reduce by throwing some details out of this model, reduce it to a discrete abstraction, which is only described by a finite state machine of sorts, then we could use algorithmic solutions to design controllers that later on we could refine in the form of hybrid controllers for the original system. And the key here is that of abstractions. So how can you reduce one complex system into a simpler one by throwing away superfluous information that you're not interested on for the problem that you have at hand? In our case, this abstraction that we are going to be chasing is the following. We're going to have our full-fledged event trigger control system or periodic event trigger control system, and we want to abstract this into a time automaton that only retains information about how the timing of this system looks like. And we don't really need to know the continuous trajectories of the system. We just are interested on the timing of it, because that's what we need to solve questions or to either to synthesize schedulers or to solve some of those questions about the performance and the metrics of the system. So the idea then will be, when we go to solve this scheduling problem, we will take these ugly definitions of my event trigger controllers and replace them by the abstractions, which I will place down here. And now, what are the type of abstractions that we will be using is what is known as a quotient system. Now, for that, let me unfold this image, which will help me to explain what this quotient system will look like. The quotient system of our original timing system, which was infinite, will be one system in which we replace the state space by a partition of the state space. So now the states of my system are going to be regions. So that would be a finite set of states. So think of it as the conic regions in this picture over here, right? So now I have only 20 states instead of having an infinite number of states, which are contained in R2 in this case. The next thing that I will do is construct transitions between those regions by saying, well, you can go from region 13 to region 15 if there's some point in 13 that when it triggers, after its triggering time is mapped to a point in 15. So the next sample is in region 15. And the last thing that I will do is associate outputs, right? So I need to associate, also describe what's my output map, associate outputs to the states. In this case, the states are regions, and therefore I cannot associate only one time as the output, but I will have to pick a time interval, right? So what are, for all the points in here, what is the set of possible times at which they may trigger? And that's those time intervals over here. This is representing, by the way, the transition relation. So from region 5, for instance, you could go to region 5 or to region 6. Now, what's important is that this abstraction, this quotient system that I was describing before, is actually semantically equivalent to a time automaton. And this can be seen in a rather simple way by looking at the example that I showed you before. Basically, think of these locations as regions of this partition. And transitions are telling me, after the sampling time, where will I end up? This clock is the one that is going to dictate how long until the next sample, right? And by using these guards and these guards and these invariants, I'm basically stating the following sort of statements. I will say that my system remains in one location, so it cannot trigger in between 0 and the minimum time associated to that location. It will leave, or it may leave, anytime in the time interval associated to that location, and it's certainly forced to leave when it reaches the maximum time. Right? So this system, something I probably forgot to mention, is that guards and invariants and guards are telling me when things may happen. And in that sense, this system is non-deterministic, right? But certainly, if you reach the end of your invariant, then the system needs to take a transition that is enabled. Otherwise, it will become blocking, and the execution of the time automaton will be frozen. It cannot keep moving farther. Now, main message is that the abstractions that I was proposing are semantically equivalent to time automata. Now, what will be then the abstraction approach? The general procedure will be basically consist of 3 steps. The first one will be partition the state space. And the main question is, how would you partition the state space? The second step, not necessarily in this order, as I'll show in a second, is to assign time intervals to those regions. And finally, once we know these are the regions that are going to be involved in our abstraction, and these are the time intervals, then we will need to do some reachability analysis. So where does this region map after that amount of time to decide what is the transition in this time, the possible transitions in this time automata. Now, at this point, one could think of two different alternatives of how to do things, and it's related to which of these few steps one takes first. So the way we originally started, which is kind of like the most straightforward way, is to say, well, let's start by partitioning the space, and then we do some computations to figure out for each of those regions what are the possible the time intervals that event trigger controller will be generating. And that can be found, for instance, in these first two references down here. Now, the next way in which one could do things is to flip the order of these things and say, well, why not partition in time and then figure out for these time intervals which regions of the state space are the ones generating such timing events. And that's what is related to the notion of isochronous sets and what we have been exploring in our most recent work. The idea is that the first alternative lets you pick which areas of the state space you're interested on. And in the case that you want to also analyze some temporal logic properties or analyze through which parts of the state space your system goes through. On the other hand, the second approach, the one of partitioning time first, allows you to tame the course of dimensionality. Because if you partition space, you usually may have three-dimensional space, and if you need to chop it in thin areas that you're interested on, you naturally suffer from the course of dimensionality. With higher dimensional systems, you'll get much more a much larger amount of states in your abstraction, which will make it also harder to compute things on it in terms of computing time. But time is a one-dimensional thing. So if you partition time, you will have as many states in your abstraction as those times that you partition the system on, and therefore you could potentially tame a little bit the course of dimensionality. Now, the drawback is that this may result in very ugly complex partitions that will make hard to perform reachability analysis. So in practice, usually what we do is some sort of combination of those two approaches. Now, to ground things a little bit, let me show you a couple of examples. So this is done for linear, we have been doing this for linear time invariant systems, and here I'm only showing you the case in which we partition first in an educated way the state space as cones, as I showed you in the previous example, and then computed the inter-event times, represented here by the minimum one will be these stars. So the distance to the origin is basically the minimum intersample time associated to that cone, and the circles, the distance to the origin, denote what is the maximum inter-event time that a point in that cone will exhibit. Now, as you can see, two different systems show different timing intervals, elongated on, they become larger on different regions for each of them. We can do this also for nonlinear systems, and here you have a second order, a two-dimensional system in which we partition time only in three intervals, and but additionally we use 16 cones. So we did this mix of both approaches that I was mentioning before, which resulted in this sort of partition of the state space and this kind of transition relation. We can, and this will be the times associated to each of the regions. We can do this also for larger systems, and this is again a nonlinear system, but in this case three-dimensional with a somewhat more complex triggering condition. And again, now you see, well, that you get a more complex set of transitions between regions. Also, you have regions where the timing intervals become more conservative, other regions where they become quite tight, as represented by the distance between these two blue and red lines. Let me move forward in the benefit also of time. And let's try to get now to the last and probably most interesting part of the talk, which is, well, okay, now you showed us how you can construct models of event trigger controllers, which only give me information about the timing, but what can I do with those models and how do I use them? So the first problem that I was promising to solve was that of scheduling, of designing schedulers, and this can be done now in a rather simple fashion. So what will we do is just replace the controllers, as I already illustrated earlier on, by their corresponding time automata. But now I need to add to this time automata model some actions that the scheduler can use to actually do some scheduling. And what could be those actions? Will be things like forcing early triggering. So saying, well, you're in this region right now, instead of waiting until your event, your triggering event happens, you may want to trigger, after just 100 milliseconds. Or you could do something a bit more fancy, which would be, well, instead of using the triggering condition that you were using, change to this other triggering condition, because that way you will transmit a bit later, and then you will prevent having a collision with the other control loop. Now, either of those two actions, which are essentially changing the event trigger control system, will retain stability. This is just kind of as a remark to just highlight the fact that by doing that, I'm not losing stability. Now, the next thing I need to do is somewhat model the network so that I can capture the situation in which two transmissions are happening at the same time, which is exactly what I want to prevent. And the way we'll do it is by, well, model my network again as a time automaton, and this model can be something as simple as the following. You have an idle state when nobody is using the network. Whenever one of those loops decide to access the network, then the network moves to a state in use, and it remains in that state in use for a fixed amount of time, the time that it takes the network to deliver the message, after which it goes back to idle. Now, if while in use another control loop tries to access the network, then the network goes into the mode bad, which is just saying, well, there was a collision. And this is the mode that we want to actually prevent. Now, how then we solve a problem of scheduling is by composing these three time automata into a very large one, which we'll call a network of time game automata. Again, because now we have actions that one can use to kind of constrain the possible moves of this large time automaton. And now we will solve, by using those actions, a problem of safety. And the safety problem is that of preventing this composed system to enter a state in which the network is in the bad state. Now, fortunately for us, this is something that the people working on time automata from the computer science side of the research have been doing already for a number of years, and there's even tools like UPAL, in this case UPAL-TIGA, that allows you to solve these kind of games. And that's something that we did. We implemented this. We used these two systems that I showed you earlier on, these two linear systems, and we allowed now these systems to change between different triggering conditions, in which the triggering conditions were different values of sigma. That gives us somewhat more complex time automata. Whenever a transmission happens, the network is in use for 5 milliseconds. And then we asked TIGA to synthesize a scheduler for us. It did that. And then what it looks like, these are the trajectories that resulted of the system. So you can see that both systems are being stabilized. One is denoted with dashed lines and the other one with continuous lines. You can see that is indeed an event trigger controller, because over here, for instance, you see that it took longer to update than over here. And here you see what are the scheduler actions. So top and bottom are one and the other control loop. And the height of the bars is the action of the scheduler telling the control loop to use one of those three triggering conditions. So we can solve already the scheduling problem. Now let's move on to metrics. what will be a performance metric that one will be interested for event trigger control systems? And here I'm going to shift attention to periodic event trigger controllers, whose dynamics can be represented by this simple discrete map. Basically, this is the state transition matrix for a given number of samples. So k number of samples times h, the sampling time. And this is basically represented that this is the state transition matrix of that system. Now, we'll have now a triggering condition that will tell us how many samples, after how many samples we need to trigger, right? So, and that will be given by this kind of quadratic condition. I don't want to get into details about this, but basically, we'll say whenever this quadratic condition becomes bigger than 0, then you need to transmit a new sample, and this will give me a value that is a natural number between 1, so next immediate sample, or k bar, many samples in the future. And now the metric that we will be interested on will be the minimum average intersample time, because this will tell us, and I'll describe in a second the equation down here. It will tell us, well, the smaller this minimum average intersample time is, the more resources in terms of communication that my event trigger controller is using. So what is the minimum intersample, average intersample time? Well, minimum will be the minimum across all possible initial states of our control system. And the average intersample time is what the word says. So we'll take the sampling times, add the map, divide by how many of them we have, and then we'll take the lim inf. So basically, the MIST, the minimum average intersample time, is telling me if I take an infinite length trajectory of my system and I look at what was the average intersample times, what is that number? And if I then look at all possible infinite length trajectories of my system, all possible labeled by the initial condition, what is the minimum of all these average intersample times that one can observe? Now, at this point, I need to introduce yet one more, somewhat a bit more complex, but not so much more model, which will be, if you think about it now, when we have time partition when we have periodic event trigger control, time is partitioned. Therefore, you can only take a finite number of values. So it's a discrete set. It can be, say, 1, 2, or 3 are the possible intersample times that I have. So technically, we don't have any more time automata. We have just a simple automata. And what I will do is introduce some labels in this sample automata over which we will be reasoning. So now the state of my system will be things of the following form. It will be what are from this location, what is the sequence of the next 3 intersample times. So if you're in this location, 1, 2, 2 indicates that the next sampling time will be 1 after 1 sample. The one after that one will happen after 2 samples, and the one after that one will happen 2 samples later. Now, the output of this state will be exactly what is the next intersample time, 1. And what I will do is push that output actually on the transitions. So from this location, you can go to this one or this other one. And what I'll do is that output 1, I'll push it as a weight on these edges. Now, notice that in this kind of model, transitions are also need to respect the so-called domino rule, right? So if we're in a location where the sampling times are going to be 1, 2, 2, then the next location necessarily need to start with 2, 2. And now, if you look at how this looks in the continuous space, in the actual space of my control loop, well, to each of these regions, to each of these locations, there will be some regions associated. And these will actually look as cones, as a matter of fact. So that means any point in this cone over here will trigger after 1 sample, then 2 samples later, and then 2 samples later. And that means that necessarily we'll have to go next to either this region or this region or this other region because of this domino rule that I was mentioning before. Now, take on my word that we can construct such models, and not only we can construct such models, we can actually construct a sequence of models that go refining, giving more precise models. And let me, this is related to what is known in the literature as L-complete approximations. Let me illustrate this with a very simple example. Imagine that we start with just a model where we only look at what is the next sampling time. So I'll have just, and assume that the next the sampling times can be only 1 and 2. Then we'll have a very simple model, which will be, well, you have a region which says the next sampling time is 1, and another region which says the next sampling time is 2. And potentially you will have all these possible transitions. So if you look at this model, it's not really very informative, because it's just telling you, well, wherever you end up, wherever you start from region 1, you know that the next sampling time is going to be 1, but after that you don't know anything, because it may be that the next one is 1, or it may be the next one is 2, and the same thing happens for 2. So what one could do is naturally, well, let's refine this. How can we refine this? Well, let's add a bit of a more foresight. So we'll say, let's take now length 2 sequences to partition my state space. And now we see how this new model starts to refine a bit and give me a bit more information. So now we know that if we start in this region, the next sampling time is 1, but the one following it is necessarily 2. So it cannot be 1, 1. So we already ruled out part of the possible futures that this simpler model was providing. And we can do that by extending them to 3, 4, 5, and so on and so forth. The more length that we add to our system, the more states that we will have, but the more spurious, non-real sampling trajectories that we are trimming out. And sorry that I need to speed up a little bit. I see I'm running out of time. At this point, to compute performance metrics, what we can do is compute then this lim average. So what we want to do now is compute exactly this MIST, but now we will be computing the MIST over these type of objects, these abstractions that I was talking about. Unfortunately for us, this is a problem that again was studied quite a long time ago, and CARP provided an efficient algorithm which actually is polynomial on the number of transitions and states, which can compute such limit average for the abstraction. And how we are going to use this is essentially in these 3 steps fashion. We'll first construct an abstraction, then use CARP algorithm to compute the lim average for that abstraction. Then we will check if the trajectory that was giving us the minimal, the minimum that MIST for the abstraction actually can happen in the original system. And if it can happen, then we are done, because we know, well, this is the worst case and we have found that value. If not, then we will be detecting that this is an spurious possible trajectories of sampling times that was introduced by our coarse way of abstracting. We will refine the abstraction and repeat the process. Now, this doesn't have a guarantee of terminating, but let me show you a couple of examples. We did this for a 2-dimensional system and for a 3-dimensional system, and you can see this first row is indicating what was the length of the sequences that we had on each of those states. And you see that, for instance, for 0.5, after taking a sequence of 10, then the algorithm terminated, and we know that exactly the MIST of this system is 0.3. And for when we pick sigma equal to 0.1 in the triggering condition, the algorithm, after taking even length 50, didn't terminate. But fortunately for us, we can compute a MIST, so a lower bound for the MIST, and even say how precise this will be. And note, of course, that the larger we make this L, the longer it takes to compute these values in general. Similarly, this can be done also for 3-dimensional systems, and of course, times become larger because now we'll have our abstractions will be much larger in space. Now, the last question I wanted to address is if event trigger control is optimal. And to do that, I'm going to retain this performance metric of mice and consider that's what we want to optimize. We would like to have a periodic event trigger controller that makes the mice as large as possible. And now we need to have some sort of action. And the action is, well, when do you trigger? So this PETC with actions that I'm going to consider now is simply saying you can let the system run all the way till its event trigger, till an event will be triggered. So the event trigger control deadline, or you can decide to trigger communications earlier than the time when the event will happen. Now, by doing that, we're respecting always the deadlines of event trigger control. Therefore, the prescribed control performance is retained. Now, what is interesting to notice is that given this PETC with actions, an event trigger controller will be a greedy optimizer. It will be the one that at every time, after every sample, will wait for as long as it can until the event is triggered. So in order to optimize these mice, an event trigger controller, it's a greedy optimizer. And in general, we know that those are suboptimal. Now, fortunately for us, again, we could simply use the abstractions that I showed you before and say, well, now we're going to solve a mean payoff game. And the interesting thing is that it has been shown that for this class of problems, the strategies for mean payoff games will be positional, meaning they're static. And in practice for us, this means that the optimal sampling to optimize the mice can be attained by specifying the next sampling time, only looking at what was the last sample acquired by the system. So we implemented again this, and this can be found in an archive paper that hopefully will be published soon. And as a simple example, this is a system in which with the green we are denoting the sampling trajectory and sampling times trajectory of a periodic event trigger controller, so the greedy optimizer. In red, we denote what are the deadlines that we will get for a given sample, so the PETC deadline. And in yellow, we denote the times at which our optimized strategy decided that we should trigger to optimize in the long term the mice. And what you can see is the following. So in the beginning, our strategy, the optimal strategy, is following exactly the greedy approach, doing the same as PETC. But around this point, PETC triggers at its deadline, the red bar, while our state-dependent sampling, the optimized one, decides that you should trigger a little bit earlier. And by triggering a little bit earlier, what it achieves is that the next sample gives us a much larger deadline, which again, we're not going to respect. We're going to transmit a bit earlier. And in comparison, the periodic event trigger controller will be generating very short deadlines, again, to transmit. So we'll have by transmitting at this point a little bit earlier, we avoid this sort of burst that periodic event trigger controller will have. And in general, what you see is that the difference is that these yellow dots stay at much larger values, while the periodic event trigger controller, the greedy optimizer, remains having this very burst, short bursts of communications, which deteriorate the mice. Now, with this, I would like to conclude, and sorry for the extra 5 minutes that I think I took, with a little recap and outlook. So first, let me give you an outlook of things that we are looking into and things that we think that can be done. The first one is to extend the modeling to use price time automata, and this is something that is somewhat related to this last part of the talk that I just showed you, to establish some sort of trade-off between convergence and communication. So there's also this notion of price time automata in which you can add cost to transmissions, but also to locations. And in that way, we think that you could establish some sort of trade-offs between how fast your system is being stabilized and how many communications you're using. The next one is some also work in progress, which hopefully will be published very soon at the upcoming CDC. and is the use of interval Markov chains to abstract stochastic event trigger control systems. So in the whole talk today, I've been only talking about deterministic event trigger control systems. We can deal also with event trigger control systems where there's some sort of uncertainty, but this uncertainty is deterministic, so there's no probability distributions involved. And this extension basically extends the work that I've been showing you of abstractions to abstract also to event trigger controllers where noise may be characterized by probability distributions. The next thing we are also looking into is how to exploit the abstraction structure, so the specific form that our time automata have in order to scale up scheduler synthesis based on time automata. And this is because this scheduler synthesis that I showed you scales quite poorly with the number of clocks, scales actually exponentially, and the number of clocks in our scheduler synthesis problem is exactly the number of control loops that we want to schedule. So the moment that you have 3, 4 control loops that you want to schedule, these time automata techniques start to break down precisely because you get an immense amount of states that you need to deal with. But fortunately for us, the kind of time automata that we are constructing have a very peculiar structure. Right? You saw that with the guards and the invariants. They had a very special structure that we are hoping that we can exploit to do more efficient scheduler synthesis. We're also looking into employing stochastic techniques for the synthesis, so some form of learning to scale up also the metrics computation and the synthesis of these last techniques that I showed you. We have been also implementing these over wireless protocols that truly try to exploit the benefits of event trigger control, and this has resulted in what we call the wireless control bus, which is a collaboration with the University of Trento. And again, this is a paper that should be published very, very soon. Can be found already on the archive. And finally, but last but not least, we're working on construction of a whole tool chain, going from abstraction, composing time automata, synthesizing schedulers, and even simulating these schedulers on a real network simulation platform given by Omnet++. And I'll invite you to keep an eye on our software page for those developments. You can find already some parts of this code, particularly the composing, but we hope very soon to release at least the first 3 parts of the chain. So in summary, I showed you how to schedule a periodic event trigger control traffic, and I hope that I convinced you that this is an interesting problem that is also rewarding to solve. I showed you how this can be done by using symbolic abstraction approaches, in particular through using time automata theory. And I also showed you that there's ways in which one can compute nowadays metrics for event trigger control and even optimize them by solving mean payoff games. And with that, I hope that we have managed to take the elephant out of the room and bring him at least partly back into the wild. Thank you for your attention. My apologies for the extra 5 to 10 minutes that I took. And I would like to thank especially my former and current students and postdocs that I show in the slides: Arman Sherifi, Diki Askija, Anchifu, Yanis Elimpautadakis, and Gabriel Glaser, and the funding sources, most especially the ERC, the European Research Council, also the Chinese Scholarship Council, and MDO. I will be very happy to answer now questions. I see that there's some action on the, there's nothing on the.
Thank you so much, Manuel. So we virtually applaud you. Please, if you have questions, press the button with raised hand. I see no questions currently. So maybe I will start with a brief question. This theory perfectly works for linear time invariant systems, right?
Yeah.
Can you please outline the class of nonlinear systems to which it can be, to which those regions and so on can be computed?
So as a matter of fact, so the simple one is homogeneous systems. I don't know if I have it here on my slides, the description of homogeneous systems. I don't have it, but basically this is a somewhat a generalization of linear systems in which what you have is that for the purposes of event trigger control, as you go farther away from the origin, the system becomes faster, and therefore times scale by shrinking proportionally to how far away from the origin you are. But there are procedures to homogenize systems that are not homogeneous naturally. So we have, as a matter of fact, done this for systems that are also non-homogeneous themselves, and this doesn't even restrict you to only consider polynomial systems. Of course, things become more hairy, more complex, and also more conservative, particularly when it comes to doing the reachability analysis, whereas what I will argue that the bottleneck is and what imposes most limitations. Did I answer your question?
Other questions from the audience, maybe? People are very hungry, probably. They want to have a lunch.
Oh, there's a person raised their hand.
Please, Miguel.
Yes, thank you, Manuel. It was a very nice presentation, very inspiring. I have a small question about the performance metrics. You talked about the bandwidth consumption, also the energy efficiency, and I missed a little bit the tracking error, the minimizing of the tracking error. I don't know if it's considered also in the performance metrics or what other variables. Mm-hmm.
I see how that was kind of rugged and swept under the rug. So basically, when I was, let me see. Yeah, when I'm optimizing, for instance, in this slide, when I was talking about optimizing the mice, I'm always doing things by respecting the deadlines imposed by the periodic event trigger controller. And by doing that, if you remember on this slide, I was saying the performance, the prescribed performance and asymptotic stability is guaranteed as long as you guarantee that you respect this condition. And this is your triggering condition. So basically, everything I'm doing is respecting this given triggering condition. And the triggering condition is giving me the prescribed performance, which is things like, which is basically what's your rate of stabilization of your system. And if you're doing tracking, which what I will do is just recast a tracking problem as one of stabilization by just you're stabilizing the tracking error. What you're doing is by enforcing a given triggering condition, you're guaranteeing that you are, whenever your tracking signal changes, you get back to it at a certain speed. Does that answer your question?
Yes, of course. So you're fixing sigma. So you're starting with a triggering function. You're fixing sigma, and you're
so sigma is fixed and gives me a given performance. But when I'm doing scheduling, I could also decide to change sigma, right? Okay. And then that will give me different performances. But I will always know that if I pick the largest sigma, that's giving me the worst case performance that I'm always guaranteed.
Okay, that was it. Yes.
And of course, this also connects to this part that I was pointing out here. So if I will be changing these sigma values, then you can imagine that these different locations are related to different triggering conditions that I was using, and they give me different performance measured through some running cost. And now I could, by solving problems on price-timed automata, I could establish some sort of trade-off by how much I communicate and how fast I'm converging.
Okay, okay, thank you. Only a small demand. Could you please put the slide where you have your URL of your software resources of your team?
Oh,
Because I
sure.
want to. Yeah.
So if you go to my website,
Yeah.
you just navigate to software. I don't know if maybe I can even show very quickly. I said like it's not yet. Most of this is not yet there. I don't know if this is gonna open now my browser. Then not everything is there.
Yes, but
it will appear there at sometime soon. So we're working around the clock on getting it ready. But if you go under research software, then yeah, then you see all the different software that we have been creating. And right now there's only one little part of that is available. There's a bunch of, there's this part is Python to Upal. There's a bunch of other tools related to other research that we are doing, but soon there will be here a link to the tool that we're creating.
okay, thank you. A huge amount of work. Yeah, I will take a look on it. Thank you, Manuel, very much.
Thank you.
Any other question? Okay, if there are no questions, thank you so much, Manuel, for this brilliant presentation, and actually the results are really impressive. So this session is closed, and I think that we have meet again after the lunch. Thank you.
Thank you. Have a nice lunch, everybody. Bye.
Bye.